Hello! Inspired by Ben Eder's great video series about an 8-bit computer on breadboards, I built my own version. In this video I want to talk about the memory and the memory address registers to access certain addresses in that memory. For the random access memory I use a single chip, which is a 628128. That provides me with 128K bytes of static RAM, so I don't need to do any refresh cycles. And so it has 17 address lines and of course 18 data lines. But in my build I effectively use only 16 address lines, so I use two 8-bit registers to access the RAM chip, or four 4-bit registers depending on the address register. And address line 816 is tied low all the time, so I effectively use only 64K of addressable RAM. In fact, I have some ideas how to use the other half of that RAM chip, but maybe I'll tell about that in a later video, but for now it's only 64K, which is addressable in my build. Another important thing about this chip is it has two different select lines, so I can switch on or off that chip by setting CS1, which is active low, and CS2, which is active high, and the chip is active only if both lines are in their active state. To hold a simple operating system for my build, I use a read-only memory chip, which is a AT28C256. That provides me with 32K bytes of static programmable ROM. That means it has 15 address lines and of course 8 data lines to access the data on the chip. The address lines are handled by the build differently. Two of those, A13 and A14, so the upper two address lines, are manually selectable. I have divided that chip into 4 different ROM banks, so I can choose which version of my operating system I want to use at start by changing the switches. And A0 to A12 are controlled by the CPU, so that makes 8K of addressable ROM during the runtime of the build. I have two buses in my system. One is the data bus that is available also on a Ben Eder system, and it's a bus for reading or writing data, and it is the 8-bit data bus connection to all the registers and the ALU on the CPU. The address bus, on the other hand, has only read capability from the view of the memory, so there are only addresses to be read, and it is 16-bit wide, so that 64K of RAM are addressable. In contrast to Ben Eder's build, I use multiple address registers for different purposes. Those address registers are 16-bit address registers, and they are connected to the address bus. There are the program counter, the new address, which is the transfer registers, and there is a stack pointer that also has a direct connection to the address bus. The first function of the program counter is to be able to increment its internal 16-bit value by 1, which is always done when the program skips to the next instruction or the data byte for an instruction. And for that, the program counter puts its internal value on the address bus so that the next instruction or the data byte is accessible in the memory. The program counter can also read a 16-bit value from the address bus. In that way, the program counter can be set to a specific address at jump instructions or during the return from a subroutine or the return from an interrupt call. Also, it's possible to put the value of the program counter in two separate chunks of 8-bit as low or high byte on the data bus, and that is used for saving the counter during subroutine calls or during the entry to an interrupt. The design of the program counter is pretty straightforward. I used the 161 counter chips, which store 4 bits, and so 4 of those counter chips make up a full 16-bit address. The counter chip can be loaded from the address bus, so all the data input lines are directly connected to the address bus, which is here on the left-hand side. On the right-hand side there is the data bus, and these 4 bus transceivers connect the program counter value either to the data bus to output the high or low byte of the program counter to the data bus, or connect the program counter to the address bus to output the current value to the address bus. These are the 4 counter chips of the program counter, and here you can see the bus transceivers for the data bus, and these are the bus transceivers for the address bus, which is going up to the memory in this way. So the flickering LEDs, of course, are the current value of the program counter. Like the program counter, the stack pointer is capable of incrementing its internal value by 1, and that is done whenever one wants to remove a value from the stack, because my stack grows downwards. But it can also decrement its value by 1, and that is done whenever one wants to insert a value into the stack. So whenever the stack pointer puts its value on the address bus, the memory points to the current value of the stack. The stack pointer can also read its 16-bit value from the address bus, which is done whenever the stack pointer is going to be initialized, for example at program start. And it is also capable of putting its high or low byte to the data bus, which is done whenever one wants to save the stack pointer for which purpose ever. The stack pointer consists of 4 4-bit counters which can count up and down. I use the HCT 191 for that purpose. Unfortunately, that chip is not perfect. The first thing is that it has no synchronous load, so I need to combine the load line with the clock line so that the load signal is valid as long as the clock is high and the load signal is set, which means it loads the value from the data bus the whole up time of the clock. That means I can't load any values to the stack pointer that change during that high phase. The other thing is that the up-down counter needs to set the down flag for counting down during the high phase of the clock, and since usually all the control lines change during the low phase of the clock, I have to use 2 clock cycles if I want to count down. So the first cycle sets the down flag and the second cycle counts the counter. The counter value can be put on the data bus through these 2 bus transceivers and can be put to the address bus through these 2 bus transceivers. This is the stack pointer. You can see the flashing yellow LEDs. This is the state, and these are the 4 counter chips that hold the current value of the stack pointer. The data bus is connected through these 2 bus transceivers with the stack register, and on the other side these 2 bus transceivers connect the stack pointer to the address bus. These are these blue lines that go up to the new register. And this is the NAND chip for the load line of the stack pointer. The new address register is a transfer register between the data bus and the address bus. That register can read the low byte or the high byte from the data bus, and thus is the only register in my build that is able to read data from the data bus. That way it can construct a 16-bit address out of two separate 8-bit values, and it is also capable of saving two temporary 8-bit values in the same register. It is capable of putting those values back to the address bus so that from those two 8-bit values there is a single 16-bit value which can either access value in memory directly for certain addressing modes, or it can transfer that address to the program counter or the stack pointer, while these two registers are capable of reading the value from the address bus. But it can also put its low or high byte back to the data bus, and I use this to restore those temporary 8-bit values, and that gives me two internal registers I can use for some more sophisticated functions in microcode. The transfer register, or how I called it, new address register, stores two 8-bit values in these two 8-bit flip-flop chips. I used the 377 for that purpose. The value can be put out to the address bus via these two bus transceivers, and on the other side the value can be loaded directly from the data bus, so the data lines of the flip-flops are directly connected to the data bus, and the data from those chips can also be put on the data bus through these bus transceivers. So these are the two register chips that hold the 16-bit value of the new address register, and these are the bus transceivers to connect the new address with the data bus. This is the part where the new address register is connected to the address bus, which is going down to the stack pointer and going up to the program counter, and again the flickering, in this case red LEDs, are the current value of the new address register. The addressable 64K bytes of memory in my build are set up from 64K of static RAM and 4 banks of 8K ROM, which is a manual bank switch, so there is only 8K of ROM during runtime available. The configuration for this memory is there is RAM for programs available between 0 and E000, and there is ROM between E000 and the rest of the address space. So a program can only access an amount of 56K of RAM, but the stack area is placed underneath the ROM area, so that whenever the stack is accessed, the ROM is unavailable and the CPU grabs from the remaining RAM that is behind the E000 area. This is accomplished by using a 4-input NAND gate, which is the HCT20 chip that I use in this case, and it has 3 address lines, which are the highest address lines, A13 to A15, and the stack control line, which is active low, and that means that gate, that HCT20 gate, has only a 0 on the output if all of those 4 inputs are 1s, and that means only there is 0 on the output if A13 to A15 are active. That means we are in the address range above E000, and the stack line is not active. SO is active low, so that means the stack is only active if SO is negative or is low. So whenever the stack is active, stack is SO is 0, the output will be 1. And that is used to drive the chip select lines from the ROM chip and the RAM chip. And we remember that RAM chip had a second chip enable line, which is active high. That means whenever the output of that NAND gate is low, the ROM chip is enabled, and whenever it is high, the RAM chip is enabled. And that way, the CPU can address the same address space twice to grab ROM bytes or to get stack bytes. Benita's 8-bit computer has a manual programming mode that allows to change bytes in memory, and he used it to enter programs into his computer. My programs are loaded from an SD card, but I use that manual programming still to check memory values during debugging or to correct memory values if I see there is something strange in memory during program testing. So I switch to program mode by stopping the CPU clock and then use a single toggle switch, and there is a red programming mode LED that lights up when I'm in program mode. Then I can select the address that I want to use by using two 8-bit dip switches, so I can access the whole 64K of memory of my build, and there are 16 blue LEDs that show which address is selected. And there is a data selection which is done by an 8-bit dip switch, and there are 8 red LEDs that show the current data of that memory address or that show the value that I just put into the chip. The data write is done by a push button switch as it is in Benita's build. This part of the schematic shows the section with the RAM chip and the LEDs for the data and the address lines. Also shows the dip switches for the manual data input, and it also has the logic to switch between manual mode and control logic mode. The switch is this one, and in run mode it is connected to VCC, so in run mode this line is high, and as long as this line is high, that gate will only be controlled by the memory write signal, so the memory write signal alone decides whether this output of the gate is low or high, and then that is fed further to the write enable line of the RAM chip. On the other hand, if memory read is requested, the memory enable line gets low, and that means that bus transceiver is set into direction from RAM chip to the data bus. And also, since low input on an AND gate always sets the output low, this line gets low, and so the output enable is set active. This is active low, and the chip select 1 is activated because this is another AND gate where 1 0 input leads to a 0 output, and so the chip select 1 is also activated. If we switch to manual mode, that line gets connected to ground, so is low, and that blocks the write signal from the control logic and also blocks the bus transceiver that connects the RAM chip to the data bus, since 0 in the input leads to a 1 on the output, and that blocks this transceiver completely. The data is shown from the RAM chip through these LEDs whenever we are in programming mode, and if you want to write data into the RAM chip, you toggle that push button, which means as soon as you close the switch, that gate here will be low, and that allows the data from the dip switches to travel to the internal data lines and also activates the write signal through this path. The second part of the schematic shows the data input part for the manual programming with the dip switches and the bus transceivers that are connected to the internal address bus, which in turn is connected to the address bus that has the connection to the address registers. This is the ROM chip, which is banked through this dip switch here. There are two lines, A13 and A14, which have direct connection to this dip switch and are usually tied low. Another interesting thing is that the write enable line is usually tied high, so there is no write possible to the chip, but there is this write enable dip switch, and if that switch is closed, the ROM chip gets the same write enable line that the RAM chip gets, so that a write to that ROM chip is possible. This is the 4-input NAND gate that decides whether the RAM or the ROM chip is active. It gets as input the stack line and 3 of the address bus lines, which in this case are the highest lines that will trigger the chip select of the ROM chip. So this is the RAM chip, which is connected to the data bus through this transceiver. This is the logic to switch between run mode and programming mode. These are the internal address bus wires, which connect the ROM chip and the RAM chip with the data bus. This is the logic to switch between RAM and ROM, and this allows to switch the bank of the ROM chip. These are the LEDs for the current address, and these are the dip switches for the manual programming mode. One interesting thing about that EEPROM that I use for my read-only memory is the way that this chip can be programmed. It's not only that it allows byte-by-byte programming, so I can just put in a single byte. I can also put that in without explicitly erasing the byte or the area before. And not only that, the write process that this chip requires is very similar to the write process that the RAM chip has. That means you have to deactivate the output line, then set the address lines, activate chip select so that the chip is active, activate write enable, pull that low, then set the data that you want to write into that address, and then deactivate write enable, and at that deactivate pulse the data is latched into that chip. In the end, the only and most important difference between writing to the EEPROM and writing to the RAM chip is the wait time after the deactivate of the write enable chip. While the RAM needs about 25 nanoseconds for the data to be written into the storage, which is fast enough to be done in a single half clock cycle of my build. The ROM chip needs about 150 microseconds to store the data, which is a lot of more cycles, about 150 cycles in my build. But nevertheless, to write a byte to the ROM chip, there is no additional hardware required, but only a certain procedure that needs to be followed. That means what I do, I start and verify if the new value is identically to the old value, and if so, then I don't do anything, I just skip the value and keep it as it is. If not, I write the new value like I would write that value to a RAM chip, but then I wait a few microseconds and read that value again and check whether it is different from the value that I would expect. And if so, I wait again and try to read the value again until the value matches, or if it is still different after 256 times. After I found no different, I check again, I read the value again, and if so, if it's still different, I call it verify error and jump back to writing. And if there are more bytes to write to the chip, I start again at the first point with the new address. This is a quick walk through the code for the ROM programmer in my own assembly language. It starts by reading the byte that is to be programmed into memory, and that byte is compared to the actual value of the byte in the EEPROM, and if it's the same, we just skip programming and go ahead as if the verify was already successful. If not, then I write the byte into the EEPROM and start verifying. That means I check if the byte at the memory address is the same that I want to program, and if not, I wait for about 100 microseconds, and then I increase the try counter and start again with verifying, and that repeats until either the byte is okay, the verify is successful, or that verify loop is complete because I already tried 256 times. Then I compare again if that value is okay, and if it's not, I jump to the error code, and if so, I add 1 to the byte counter and skip to the next byte. It's a quick demo of the burning process. The current version of my OS is dated from the 27th of January. Burn OS is the command, and OS is the file that contains the new file for the OS. So it asks me to wire the ROM, so to disable the write protection. So I go to the dip switch and choose the bank to burn the new operating system into and disable the write enable the write. Then I hit G and the process starts. So the first bytes were identical, and there are some verify errors during that process because I bought cheap and old Chinese chips, and they need some extra time to be programmed correctly. So then finally the programming is done. I disable the write enable, or I enable the write protect again on the ROM chip. This is done here. I leave the bank as the new bank, so this is the new operating system that starts after that reset. And if I check the version of the operating system, you can see it is from the 31st of January. Okay, that concludes my video about the memory and the address registers of my build. As always, feel free to comment. Thanks for watching, and maybe see you soon. Bye.